Okay, in section 1 we discussed polynomial functions. In this section we're going to discuss rational functions. Well, what is a rational function? A rational function is obtained from polynomials. Actually, you see that. But let me just say something here first. Get this piece of paper. Find one. See, we have if this is all a function in the whole world, and then this part of it is one family of polynomials. Okay. And there is another family of rational functions. Rational function. As you can see, rational function family is bigger and contains all the polynomials. So polynomials are part of the rational functions. Okay. So rational functions are more general than polynomials. Family is bigger. Okay. So what we have is this. If you have polynomials, then if you take the two polynomials and then divide them, write them like a ratio, like a fraction, then the result is called a rational function. So what is a polynomial? The ratio of two polynomials is called a rational function. So this is one polynomial p of x, this is another polynomial q of x. Very simple. Because we already know what polynomials are, just find the ratio of them to get a rational function. Because we have all kinds of polynomials, as a result we get all kinds of rational functions. So here, before I give you the examples, we are looking at, in this course, we are looking at those rational functions which are in lowest form. In other words, p and q will not have common factors. Okay? If they have common factor, then common factor or common factors, then it becomes a little bit more involved. And we are trying to avoid that. So we're going to look at just those particular rational functions where p and q are relatively prime. That means they don't have any common factor. Just like numbers, you know, like if I say 7 over 13, see 7 and 13 are relative prime. This is the same thing to say 14 over 26. You see, these two are the same thing, but this one is simpler because I can divide both of these two by 2 to get that. Okay, so these two have common factors, but these don't. We say 7 and 13 are relatively prime. The same idea about rational functions. So we want p and q to be relatively prime. In other words, not having common factors. So let's look at some specific examples here. As I said, I recorded this video but didn't have sound, so I have to do it again, and I don't have a blank copy. See, I already have written on it. So I'm gonna things work out here. You see, so I'm gonna use check mark to say whether something is a rational function. This one is a rational function. This numerator is p of x, this denominator is q. Degree 1, degree 2. Two polynomials. This one is also a rational function. Numerator is 4x minus 5, denominator 2x plus 3. These are two polynomials of degree 1. Degree 1. See? This one has degree 2, so this is a little bit simpler than that. The next one is a polynomial actually, but you can give a denominator 1. So the numerator is p of x, denominator is 1 q of x. So this is a rational function. So this example shows that all polynomials are rational functions actually. Okay. This one is simpler. Numerator is just a number, it's the polynomial of degree 0, p of x. Denominator is a linear polynomial. So this is a rational function. This is a rational function, but compared with the other one, it's pretty ugly looking. It's very involved. Like numerator has degree 5, the highest degree is 5, degree 5, and then coefficients are like 7 over 11, 3.75, 2.4. Denominator has degree 7 and then has 7/5, 3.21, and square root of 13. So it's a rational function, but it's not a nice looking one. It's ugly. This one is much simpler than the previous one. X over x minus 1, p is px, q is x minus 1. If I write another one right here, w 1 over x, this is even simpler. So this is a rational. This is a rational function. It's a number, 37, so I can write 37 over 1. You see, 37 over 1, so p of x is 37, q of x is 1, so this is a rational function, and this is a rational function. Okay, let's do another example. Another example is to evaluate a rational function. We'll like two rational functions here. So I have two functions, f and g, and you want to find like f of negative 2. See, f of negative 2 actually is negative 2 squared minus 1 over negative 2 squared plus 8. I have it already. And then if you simplify, negative 2 squared is 4 minus 1 is 3, negative 2 squared is 4 plus 8, 12. You can divide by 3 to get 1/4. F of 1.2. F of 1.2, I have to replace this x and this x, both of them by 1.2. And I did. 1.2 squared over 1.2 squared minus 1 and 1.2 squared plus 8. And if you put this in your graphing calculator, you get 0.049999 something. So I rounded it up to 5. In fact, I have it here, you see. Squared minus 1, put parentheses around it, divided by 1.2 squared plus 8, parentheses around it, divide, and you get 0.0466101695, and I round this up to 0.05. Okay, that's what I get. G of 3 means in G replace x by 3. So I have 2 minus 3x, so it's 2 minus 3 times 3. 2 minus 3 times 3. Smaller. See, everything together. This is G, see. And G of 3 is 2 minus 3 times 3 over 2 times 3 plus 5. 7 over 11. And finally, g of 3 halves means in g replace this x by 3 halves. So I have 2 minus 3 times negative 3 halves, 2 times negative 3 halves plus 5. And then if I use a calculator or not a calculator, I get 14 over 4. Okay, let's see what we're going to do next. It is about domain of rational functions. We actually have done domain of rational functions, but we didn't use the word rational functions before. remember? We said that every time we have a denominator, you have to make sure the denominator is not 0. So you remove those values that makes the denominator 0. Therefore, those zeros of the denominators, they have to be removed. Okay, so if you have a rational function p of x over q of x, what is the domain? The domain is a set of all x values for which the function f is defined. This function f is defined if denominator is not 0. The only time f is not defined when f q of x is 0. So what we have to say then, the domain is everything. By everything I mean all real numbers except those numbers that makes the denominator 0. In other words, zeros of the denominator, zeros of the q of x. So if we have this function here, f of x equal to 1 over x minus 3, first you put the denominator equal to 0 to see what the zeros of the denominator are. In this case only 1. So if I put x minus 3 equals to 0, I get x equal to 3, and I have to remove this point. But that's the point that makes the denominator 0. So the domain is set of all x values except x equal to except x equal to 3. So here's the picture of it. You see, you go from minus infinity to infinity, and as you do that, you bypass 3. So you go from minus infinity to 3, and then you continue from 3 to infinity, then you get your domain. So in this case, you had one number only to remove, but you may have sometimes more than one number, depend upon how many depends on how many zeros the denominator has. Okay, so like the next example, I have f of x equal to 5x minus 1 over x minus 2 times 3x plus 7. So the denominator is x minus 2 times 3x plus 7. I put that equal to 0. Then you have to put each factor equal to 0. So I put x minus 2 equal to 0. That will give me x equal to 2. And if I put 3x plus 7 equal to 0, that will give me 7/3, and these are the 2 points we have to remove. You see, remove these. So if you draw the picture, so you have to go from minus infinity, go all the way to 2, bypass 2, go from 2 to 7/3, go over 7/3, don't just remove it, and then go from 7/3 to infinity. So the domain is set of all x values, or some of the real numbers for which x is not equal to 2, and x is not equal to 7/3. Everything else is good. So that's what you do. Minus infinity to 2 to 7/3, 7/3 to infinity. And using parentheses indicates that these points are not included. Another example, it's just like previous example, but previous example was easier because the denominator was already factored for, but here it's not, see. So again, as usual, we just set x squared minus 2x minus 3 equal to 0. Now if you can factor this, that's the easiest way. But if you can't factor this quadratic formula, I can actually factor this. You see, I can factor this as 2 parentheses like this. I have x here and x there, and I'm looking for 2 numbers that if I multiply, I get negative 3. If you add them up, you get negative 2, and those are plus 3, minus 3, and plus 1. See, if you add negative 3 and 1, you get negative 2. If you multiply them, you get 3 equal to 0. So I put each factor equal to 0. X minus 3 equal to 0, and x plus 1 equal to 0. This one would give me x equal to 3, this one would give me x equal to -1. Remove this. Remove this. So here's a picture. This is -1, and here is 3. So the domain is everything to the left side of this point, everything in between, and everything above. So we say domain D is a set of all x's such that x is not -1 and 3. And this is the same thing to say minus infinity to -1 parentheses union -1 to 3 parentheses union parentheses 3 infinity. Since you use parentheses, don't end those numbers -1 and 3 are not. Another familiar thing that we did for functions in general, we're going to do it for rational functions, and that's the concept of y-intercept. Y-intercept is always f of 0, no matter what, because the y value, the x value is 0. Because y-intercept is the point where the graph of the function crosses y-axis, therefore the x value is 0. So I put x equal to 0, what I get is that y-intercept. See, so y-intercept is f of 0, which is p of 0 divided by q of 0. So let's look at some examples. Okay. Two more examples to find the y-intercepts. I have two functions here. See, g of x and f of x. G of x, y-intercept is g of 0. I replace these x's by 0. 4 times 0 minus 1. 5. 2 times 0 plus 3. I get -5/3. F of x is this function. Y-intercept is f of 0. If I put x equal to 0, I get -3 times 0 minus 5. 0 squared plus 4 times 0 minus 5. 1. Get -5 over -1, which is 5. So easy to find x-intercept, just like we did it before. X-intercepts are similar like we did it before. You have to put the whole function equal to 0, which means that the y value is 0. So when you put the y value is 0, the x value you get is the 0 of the function. But if it's real, it would be the x-intercept. So most of the examples we're going to do here, actually, we get x-intercepts rather than having complex zeros. Okay. So here is example 5. Has two parts, A and B. We want to find x-intercept. Just one thing I have to mention is that if you have a fraction A over B equal to 0, I give a denominator 1 to it, then I can cross multiply. So A times 1 is the same thing as B times 0. That means A equal to 0. So A over B equal to 0 is the same as A equal to 0. So that means that reduces the amount of work you do. You can put A over B equal to 0 and then multiply both sides by B to get that, and then A equal to 0. But at the beginning, you just put A equal to 0. That reduces the amount of work. So in other words, put the numerator equal to 0. So of x equal to 0. Again, I'm going to turn off these slides to maybe make it a little bit clearer to see what's happening. So that put the numerator equal to 0. Numerator equal to 0. So you say x squared minus 25 equal to 0. You can factor this as x minus 5 times x plus 5 equal to 0. For those of you who remember this formula here, difference between two perfect squares. So if we have u squared minus v squared, then you write u plus v and u minus v multiply. So you get factorization. Okay. You studied this in intermediate algebra. 25 is 5 squared, so x squared minus 5 squared. So you say x minus 5, x plus 5. Put x minus 5 equal to 0. It gives you x equal to 5. This is one real 0. And put x plus 5 equal to 0. Gives you x equal to minus 5. So these are x-intercepts. Because they are both real, they are x-intercepts. This one, I put the numerator equal to 0. So h of x equal to 0. I put x squared minus x minus 2 equal to 0. And I can factor this. Factor it like this. I have x here and x there. Then you're looking for two numbers. They add up to minus 2. The product is negative 2. So it's minus 2 and plus 1. You see? So if you work this out, you get this back. So this is a factorization. If you can't factor, then use quadratic formula. I'm not going to use quadratic formula, okay? Because I can factor it. If I can factor, that's easiest. Why should I make my life more difficult? So x minus 2 equal to 0 gives you x equal to 2. This is one real 0. X plus 1 equal to 0 gives you another real 0. Both real, so they're real. So that means x-intercept. This example put f of x equal to 0, so that means set numerator equal to 0. This 7 equal to 0. That's contradiction. Impossible. So that means no x-intercept. If it has no x-intercept, it may have complex zeros, but I'm not going to make any attempt to find them. Okay, as I said, may not, who knows? Yeah, actually, if you want to, you have to go through the process. So in this case, it doesn't actually. It doesn't have complex zeros, and it doesn't have real zeros. But there are situations, maybe your graph or your function, rational functions, doesn't have x-intercept or real zeros, but it may have complex zeros. Okay, but not here. I said may. See, but I'm not gonna go any further. Okay. The next concept we're going to discuss here is the concept of asymptotes. See, we got it big for you. See, asymptotes. You don't pronounce that P. Asymptotes. What is an asymptote? The best way for me to explain this, think of let's say Joe and Joe and Bob. Joe and Bob are friends. In other words, Joe just met Bob a few days ago, and they spend a lot of time together, become really good friends. So as time goes on, as t goes to infinity, t is time. As time goes on, Joe start behaving like Bob, and that actually happens. You know, if you spend enough time with somebody, if Joe spent enough time with Bob, then eventually Joe is going to behave like Bob. Okay, but that's what we are trying to do. The idea is this. Let me go back to function, then go back to Bob and Joe in just a second. See, if we have a function here, you know, like it goes up and down, and then like this, and then sometimes I put arrow here. You see, the question is, what happens if this arrow goes forever? Because it goes to infinity. I have no idea what happens at infinity, because infinity is not a place I can go and find out what happened to this end of this graph. Okay, it doesn't matter how far out you go, this is x going to infinity, still a lot more to go, so you never get to the end. So you really never know what happens to this arm of this, whatever this function is. Or if you go to the left, x going to negative infinity. Okay, so that's the idea. We want to know what happens in terms of polynomials. As you remember, it goes maybe there are 4 situations, as you remember: up to the left, up to the right, up to the left, down to the right, down to the left, down to the right, down to the left, up to the right. Okay, so but for other functions we don't know. Like if you have irrational functions, how would these arms behave? As you remember, as I said one more time, for polynomials, you see, it could be like this: up to the left, down to the right, or up to the left, up to the right, or down to the left, up to the right, down to the left, down to the right. You see, this is for polynomials. But if a function is not a polynomial, then what can you say? Like if I have a rational function, okay, then what can you say? So I really want to know what happens to the graph of this function as x goes to infinity. Okay, or sometimes x approaches a particular number. You're going to see that examples too. So let's go back to this example of Bob and Joe. If Joe is a younger person, meets this older person, so this because he's younger, and if this person spends enough time with Bob, because Bob is older, then he's a role model. After a while, Joe is going to act like Bob. You see. So if Bob is a good person, if Bob is a very, like they said, Joe is my son, and then he goes to college somewhere, and somebody tells me, hey, your son Joe, meet this guy Bob, then what are you going to do about that? Then they say, well, this Bob is a very good guy, you know. He's very responsible, he does his homework, he goes to his classes, he makes good grades, he works hard, he makes money, he wants to build his future, and very good person. Then me as a father won't worry about my son Joe, because I say, okay, if Joe spend time with Bob, then Joe is going to be the same good person. Okay, so eventually, that means as he goes to infinity, time goes to infinity. Eventually, Bob is going to act like Bob. Joe is going to act like Bob. So now, if Bob is a bad person, you know, he does all kinds of bad things. He's a thief. He steals people. He hurts people. He does drugs, and he does this and that. And then I would be very, very worried about my son Joe. I said, well, because if Joe spends time with this bad person, eventually he's going to act bad. Okay, and that's the meaning of the asymptote. That so as Joe starts acting like Bob as t goes to infinity, I call Bob to be an asymptote. An asymptote for Joe. So that means a behavior of Joe gets closer and closer to behavior of Bob as time goes to infinity. Okay. So that's the meaning of asymptote. So now how can I discuss this like in terms of function? How can I write this in terms of function? So that's what I'm going to show you in just a second. Okay. So let's say I have let's say you have this function. Draw a picture here. Yeah, I even do it. Another piece of like that. And let's say this is a straight line. I want to do the dotted line. This is not the graph of the function. This is it, and this is going to be the asymptote. Let's say I have a function whose graph is like this. Right here, we don't have access to it because we're going to look at what happens at infinity. See? So let's say it's like this, and as x goes to infinity, the graph of this function, let's say, gets closer to the graph of this dotted line, like this, and then and eventually, as I go far out, enough far out here, then the graph of my function, this red one, eventually become closer and closer to the graph, to this straight line. You see, eventually, they won't touch, but they will touch at infinity. So that means as x goes to infinity, my function, the arm of my function, eventually becomes like this one. So it becomes linear because it's a straight line. So now I know what happens to the arm of this function. Okay, the behavior at infinity. As x goes to infinity, the graph of this function, this graph here is f of x. This graph gets closer and closer to this line. You see, let me draw this a little bit thicker here. Like that. So as t goes to infinity, you see, then eventually I can say, eventually f of x will act like a linear function. Because why? Because as x goes to infinity, you see, this graph becomes eventually like that. So if this is Bob and this is Joe, you see, now if Joe spending time with Bob, then Joe eventually becomes like Bob. They act like Bob. You see, Bob acting linear, therefore Joe will act linear eventually. Okay. So in this case, I say this line is an asymptote. It tells me about the behavior of my function at infinity. Okay. I may go to negative infinity. Let's say I have another function. It's going like this. You see, it's the green one. See. Now, as x goes to negative infinity, like that, then the graph of the function, you see, becomes this way. So now this function, you see, eventually is going to act like this one. So this is This is an asymptote. So what is an asymptote then? An asymptote of a function is a line, could be a straight line, could be not a straight line, could be anything. This is a line whose graph, the distance between the function and the graph gets smaller and smaller as x goes to infinity. You see, like distance between this asymptote and my function f of x, you see, the distance is getting smaller and smaller. The distance goes to 0. Like here, the distance between my green graph and this asymptote is. Okay. So that's the meaning of asymptote. So let's read this sentence here, what it says. Okay. An asymptote of a function is a line that the graph of the function approaches. Just like I said. See? An asymptote is a line such that the graph of the function approaches to it eventually as x goes to infinity, or as x goes to negative. Okay. You may have some situation like this, of course, just doesn't have to go to infinity. If I have a, let's say, a vertical line like this, okay, and then my function, let's say, the graph is like this. Let's say this point is 2. This is line x equal to 2. Okay, so I say line x equal to 2 is a vertical asymptote because as x approaches 2, you see, as x gets closer and closer to 2, the graph of the function gets closer to this vertical line like this, see, and eventually meet each other at infinity. So you don't have to go to infinity to have asymptote. You may go to a number to have vertical asymptote. Okay. Like, you know, if I go from the left, let's say I have something like see, if x goes, this is x goes to 2, x approaches to 2 from the right side, then the graph of the function meets this red one at eventually. See, they don't touch, it just follows right to it, slide against it. So this is a vertical asymptote. Vertical asymptote. Okay. Or if you go from the left side, the same thing happens. We're gonna say a different example. This is a slant asymptote. Slant means like this. This is vertical asymptote. Okay. It could be horizontal asymptote, like, you know, if I have something like if I have a horizontal line like this, okay, and then my function behaves this way. See, eventually, you see, I don't care what happens here because this is within my range, within my reach. What I want to know is where it's not within my reach. That's infinity. See, so as you can see, because this one is horizontal, this line is always horizontal, even at infinity. Therefore, my graph eventually becomes horizontal if I go far out. Like, you know, one example is, why should I go any far here? Let's say this is 6 volts. And then your cell phone, this is time. Cell phone, you used it, is almost need to be charged, is almost 0 charge in it. So it's not working, it's dead. Then you connect it to the wall, to electricity, start charging, and as time goes on, the amount of charge goes up like this. Then if you leave it connected to the electricity long enough, then your cell phone eventually becomes fully charged at 6 volts. See, like that. So 6 volts is an asymptote for your cell phone, because your cell phone, which is probably 0.01 volts, is not working anymore. Then you connect it to the wall, starts charging as time goes on. Then this graph of the charge gets larger and larger, but your cell phone never gonna go above 6 volts. Okay, so eventually, as t goes to infinity, like if you leave it hooked to the wall for 2 days, long enough, then you would be fully charged. Okay, so these are the meaning of asymptotes. Okay, so or it actually sometimes discharge. You see, let's say in the morning your cell phone is 6 volts full charge, 100%, and then you start using it. This is time t. As you use it throughout the day, then the charge goes down, down, and down, and then eventually dies. See, no charge. So horizontal. So x t-axis is the horizontal asymptote. This line is a horizontal asymptote. See? So hopefully you understood the meaning of asymptotes. Okay. Now the next page, I'm going to show you a few pictures and different situations for asymptote that may occur. Here they are. Here are some examples. I have written on some of them, but that's okay, I'll explain it again. Like this first example, let me just make it bigger a little bit. See, the dotted lines, which is this vertical one, and the parabola. These are asymptotes. And then the solid lines are the graph of the function. As you can see, as x, this is x, goes to negative infinity. As x goes to negative infinity, the graph of your function eventually becomes like a parabola. You see, like here you cannot even separate them anymore. They are different here, but if you go far out to the left, they eventually become it eventually becomes a parabola. So this function f of x, if you go far out to the left, behaves like a parabola. If you go to the right, you see, if you go to the right, then it just becomes vertical. You see, it becomes like this. So on the left side becomes a parabola, on the right side becomes vertical. This is another piece of this function. You see, if you go to the left, if you approach this point is about I think what is it, 1, 2, I don't know, this is probably 3, whatever this one is, this line x equal to 2, I think it is. This is from here to this, 4, so it's 2. This is line x equal to 2, this vertical line. So as you approach the line, as we approach this point, you see, from the right, the graph becomes vertical. If you go to the left, to the right, becomes parabola. See, so eventually means these endpoints, they're the same. So eventually, this part is parabolic, this part is parabolic, this one and this one are linear, vertical. Okay. So this is the vertical vertical asymptote. So this guy here, this dotted line, is a vertical asymptote. You see, this one vertical asymptote, and this dotted line here is parabolic asymptote. Okay. This next example, you have a horizontal and vertical. You see, if you go to the right, x go to infinity, your graph becomes horizontal, like this horizontal asymptote. If you get to point 3, this is line x equal to 3. This line here, this vertical line, is at 3. So if x goes to 3 from the right side or from the left side, if x goes to this 3 from the right side, then your graph would be shoot to infinity. Goes to the moon, goes to Mars, infinity, vertical. If you approach this line from the left side, it falls into a well. You see, goes like this. never touches it, but it just falls with it, goes all the way down, it goes all the way up for infinity. And if x goes to negative infinity, if you go that way, then the graph of your function becomes horizontal. But this is a vertical, asymptote, this is a horizontal asymptote. The same thing here, this is another example. This is line y equal to 2. Is a horizontal asymptote. This line is 3, x equal to 3. Is a vertical asymptote. Okay. Here, so this function has two asymptotes, horizontal and vertical, like this one, horizontal and vertical. This one here has a slant asymptote. This is slant. Slant means sideways or oblique. Slant asymptote. So it has a one slant asymptote, one vertical asymptote. Vertical. Okay. This one right here has a horizontal asymptote. You see, it goes up. I mean, I have no problem with around here. Around here I can see it, but eventually I want to know what happens. Eventually it becomes horizontal. So this is the horizontal asymptote. HA, horizontal asymptote. Okay. This is also a horizontal asymptote. Horizontal asymptote is x equal to, I really don't know what this number is. This is 1 and this is 1.75, I think. Doesn't matter. Whatever this line y equal to 8, whatever that number is. And this is negative 2 here actually. So this line is a horizontal asymptote. So this is the meaning of vertical and horizontal asymptote. Okay. So let's look at a little bit more formal definition of asymptote. Formal definitions of asymptote. The formal definition is this: a vertical line. I draw a picture as I write this definition. Line x equal to a is a vertical asymptote. Here we go. Line, this line x equal to a is a vertical asymptote of a function as x approaches a. This is a. This is x approaches a from the left and from the right. From the left or right, f of x goes to infinity. So as x goes as you walk toward this line from the right, or you walk toward this line from the left, then your graph of the function, if I can find my red one, approaches positive or infinity, like this. As you go from the right, maybe it just like it's space shuttle goes to infinity, goes to, maybe it falls. Maybe it goes this way. You see? Slide against it. Or maybe, and if you go from the left, maybe it goes to infinity, or maybe it goes to negative. So one of these four possibilities. Okay. And if this happens, we say we have a vertical asymptote. Now line y equal to b, the horizontal asymptote. If as x approaches to positive infinity and negative infinity, then the graph of the function approaches line B. So here is a picture. You see, I have a picture here, but I'll show you first here. You see, if this is a horizontal line, and then as x goes to infinity, as you walk toward infinity, then the graph of the function maybe comes down and slide against this line and then becomes horizontal, like that. Or from below, who knows. Or as x goes to negative infinity, then the graph of the function maybe goes like this, or like that. Becomes horizontal. So here are the pictures. Line x equal to A, line y equal to B. As x approaches this point A, then you graph, like for this particular example, goes to positive infinity, and if you approach that line from the left, then you fall to negative infinity. As x goes to positive infinity, then the graph approaches this horizontal line, or if you go to negative infinity, the graph approaches again this horizontal line. So this is a horizontal asymptote, this is a vertical asymptote. Okay? So these are we discuss the meaning of asymptote, and then we just give them some mathematical definitions. Now the question is, how do we find asymptotes? I think the previous page I said something at the bottom of the page. Let me see if I did. Maybe okay, I guess I said it here. I'll discuss it. Okay. The question then, the main question is this. Okay, I understand now what asymptotes are. I know the asymptote, I know horizontal asymptote, I understand vertical asymptote, I understand slant asymptote. Just tell me, how do I find them? Okay. This theorem tells you how to find them. So this theorem says if you have a rational function p of x over q of x, then a vertical line x equal to a is a vertical asymptote if this a makes the denominator 0. Okay, and as you can see, this number a that makes the denominator 0 is not in the domain at all. You see, so that means that when you draw the domain of a function, of a rational function, you see, like domain of a rational function, one point is missing here, one point is missing there, because these, let's say this is x equal to c1, x equal to c2. These two numbers, so I have f of x equal to p of x over q of x, okay? And q of x is 0 at these 2 points. So q of x with c1 is 0, q of c2 is also 0. So these two numbers make the denominator 0. So these two numbers are not in the domain. So the domain is like this. You see, we discussed this. Domain is everything to the left, everything to the right, between these two, and everything to the right of this. That's a domain. But this theorem says now those numbers that makes the denominator 0, I have vertical asymptote there. So that means at those points where you remove those numbers, I have vertical lines like this. So this is x equal to c2 is one vertical asymptote. This is another one. X equal to c1. So that's kind of interesting, because when you find a domain, you put the denominator equal to 0. When you put the denominator equal to 0, you accomplish two things. One of them is that you find the domain, and then the other one, automatically, you find the vertical asymptote. Because when you find the domain, some points are missing, and those are the zeros of the denominator. And at those points, I draw a vertical line, and those are the vertical asymptotes. Okay? So let me say it one more time and then go to example. If you have a function f of x equal to p of x over q of x, some numbers like c1 or c2, maybe more than 2, maybe 3, 4, 5, depends how complicated this q is. You find the zeros of the denominator. When you find zeros of the denominator, then you get points, those numbers c1 and c2 are the points which are not in the domain. So the domain, like for this particular function that I don't have any number, just assuming these are the zeros, the domain is everything to the left side of this number, everything to the right side of this number, and everything between those two numbers. But these two numbers are not in the domain. Okay, if If they're not in the domain, then at those points I draw two vertical lines, and those are the vertical asymptotes. Okay, so that's how you find vertical asymptotes. You put the denominator equal to 0. You solve for x. Those x values are the vertical asymptotes, and those x values are not in the domain anyway, because vertical asymptotes does not intersect the function. So that's what I said here. You see, the domain of a rational function consists of segments or interval of x-axis separated by vertical asymptotes. You see, this is one vertical asymptote, this is another vertical asymptote. So these two vertical asymptotes divide the whole real line from minus infinity to positive infinity to, in this case, 3 pieces, 1, 2, 3. Okay, and at those points are not in the domain. Okay, so if you have a situation when you have 5 points, you see, these points are not in the domain. Let's say C1, C2, C3, C4. The domain is like this. Everything is in domain except these numbers, and these are the zeros of the denominator. Therefore, at this point I have vertical asymptotes. You see, like one here, one here, one here, and one. So for a rational function, therefore, vertical asymptotes occurs at points which are not in the domain. Okay, so that's the theorem. So, hence, one can find the domain and the vertical asymptote by putting the denominator equal to 0. So you accomplish two things by putting the denominator equal to 0. You find the domain and you find the vertical asymptote. Okay. So let's look at some examples here to actually do this, for example. Okay, here's your first example. I start with something really simple. This is your rational function, okay? 7 over x minus 4. And it says, find and draw the vertical asymptote for each function of the graph. Also, mark the domain of the function. We are not going to graph any of them. We're just going to do it. So I say, set the denominator equal to 0. Set x minus 4 equal to 0. This gives you x equal to 4. You see? So this is a guy that has to be removed from the domain. So I go here, and this is 4 right here. I draw a hole. The domain is this piece to the right and this piece to the left. So this 4 is not in the domain. Okay, if it's not in the domain, then at this point I draw a vertical line, and that's your vertical asymptote. X equal to 4. So domain is this, therefore domain is minus infinity to 4 union 4 to infinity, and vertical asymptote is x equal to 4. Okay, that's it. Good. That's all the problem asks us to do, and that's all I do. We do more later on with them. We're eventually going to graph rational functions without a graphing calculator, and then check it with a graphing calculator. Like here, how about this example? Well, just set the denominator equal to 0. So set x squared minus x minus 6 equal to 0. I can actually factor this. As I said, if you can factor, it's easier. If you can't factor, use quadratic formula. So I have put x here and x here equal to 0. Then I'm looking for two numbers which add up to -1, you see, minus times x is minus 1 times x. And the product is negative 6, and they are negative 3 and positive 2. So I put each one equal to 0. If I put this one equal to 0, I get x equal to 3. If I put this one equal to 0, I get x equal to negative 2. Okay. So these are vertical asymptotes. What is it doing? Well, let's mark them right here. 3, here we go. This is 2, this is 4, 3 is right here. And the negative 2 is right there. So at this point, I draw vertical lines. These are the vertical asymptotes. So line x equal to 3 and line x equal to minus 2. What is the domain? Domain is pieces of x-axis between these two vertical lines. So one to the left, one in between, and one to the right. That's the domain. So let's write it. Domain is minus infinity to negative 2 union negative 2 to 3 union 3 to infinity. Okay. Let me clean my mess here. Yep. So in this case I had two asymptotes, therefore I have three regions. One to the left side of this line, one region in between, one region to the right. Good. Previous example, I had one asymptote, so you have one region to the left, one region to the right. In fact, what's going to happen, let me just be ahead of myself a little bit. When you graph a function like this, then you have three regions. You see, you have one region, this area, one region in between, and one region to the right. Then it turns out that, let me get my pencil here, so I can erase, I want to erase it. You see, when you graph this function, you get one graph here, one graph here, and one graph there. You see, and these three graphs are not connected to one another, discontinuous. You see, like the previous one, you actually get two pieces, one piece to the left, one piece to the right. Okay. Here you have 1, 2, 3 regions, so you get one piece of graph to the left, to the right. This region, one piece of graph here, and one graph there. Okay. We're gonna do that later on, but right now I'm not. I'm just saying it, what to expect. The next one, you see, this is a good one because it's already in factored form. So I said the denominator equal to 0 like this. Then if I put this one equal to 0, I get x equal to 2. If I put this one equal to 0, I get x equal to minus 1/2. And if I put this one equal to 0, I get x equal to 3. Okay. So these are vertical asymptotes. I can go ahead and graph them right here. Minus 1/2. This is minus 1, minus 1/2 is right here. So I have one vertical asymptote right there. X equal to minus 1/2. Then the next one is x equal to 2. X equal to 2 is right here. So I have a vertical asymptote right here. X equal to 2. And then 3, I have 1 here. X equal to 3. Now how many regions I have? One region to the left side of this line. 1. Another region between these two lines, 2, another region between these two, 3, and another region to the right, 4 regions. So what is the domain? First of all, domain is every number except these 3 domain is minus infinity to minus 1/2, union minus 1/2 to 2, union 2 to 3, union 3 to infinity. Okay, that's the domain. And then, as I said before, if you go and graph this, you expect to have one piece of graph on this region, one piece of graph in this region, one piece of graph in this region, one right here. Okay, you get 4 pieces for this function. The next example, you see, I set x squared plus 9 equal to 0, but it doesn't matter what x is. X squared is positive. When you add it to 9, you never get 0. In fact, if you put this equal to 0 solved, you get x complex number. But complex numbers, we don't have asymptote when it's a complex number. So the denominator is never 0. See, clearly. Clean my mess again. Sorry about that. This one too. Okay. Notice, you see. Notice x squared plus 9 is never 0. So no, so that means no x or vertical asymptote. Okay. Still not working sometimes. No vertical asymptote, and the domain in this case is the whole real line. Because nothing makes the denominator 0. The domain is there. Okay? Alright. I think I'm going to show you something. I think I didn't mention it. Is the bottom of page 42. We just discussed that when we talked about asymptote. Here I said something that I'm going to remind you. We said that okay, in this section we restrict ourselves to the study of rational functions with vertical or horizontal asymptotes. Okay, so that means we're going to consider the simplest situation. As I said before, maybe that you can spend an entire semester on rational functions and their asymptotes and so on, but that's not what we're going to do. So we're going to look at those situations for rational functions when you have only vertical asymptotes or we have horizontal asymptotes. Of course, there are situations that you may have slant asymptote or parabolic asymptote or probably more complicated asymptotes. But that's not what we're going to do. We're going to just say, let's consider the simplest situation when you have either vertical or horizontal or both. And it's very easy. This theorem shows you when you have more complicated asymptotes. So, but it doesn't matter. If it is one of those cases, we just don't go after doing it. Okay. This theorem is very important. We did vertical asymptote. You see, we learned how to find vertical asymptotes. We put the denominator equal to 0, solve for x, we get the vertical asymptote. The question now is, how do we find horizontal asymptotes? Okay, horizontal asymptotes depends. Horizontal, non-vertical asymptote basically depends on the degree of the numerator and the degree of the denominator, and that makes it maybe sometimes complicated depending upon what the degrees are. If the degrees of P and Q are really big, then you may have some complicated type of asymptotes. But let's see what this theorem says. This theorem says if you have a function p of x over q of x, a rational function, then one of these a rational function p of x over q of x has at most one horizontal asymptote. So at most one horizontal asymptote. You may not have any actually. Okay. So if it does have, it has one only. You may have more than one vertical asymptote. Like this one has two, this one has three, the previous one had one. But when it comes to horizontal asymptote, there is only one horizontal asymptote. Okay, and that's what this theorem tells us how to find it. So to find the one and only one horizontal asymptote, look at the degree of p and look at the degree of q. Three things can happen. The degree of p may be smaller than the degree of q. Okay, something like this is the next example. You see, like this situation here. You see, the degree of the numerator is 1. The degree of the denominator is 2. So 1 is less than 2. So the degree of the numerator is smaller than the degree of the denominator. That's the case. If that's the case, then y-axis, y equal to 0, which is x-axis, is the horizontal asymptote. Okay. So if degree of p is, let's say, 4, but degree of the denominator is 7, 4 is less than 7. So x-axis is the horizontal asymptote. Y equal to 0. What if the degrees are equal? Then what can you say? If degree of p is less than q, x-axis is the horizontal asymptote. What if the degrees are equal? Okay, something like this this example here. We're going to look at it in just a few minutes. See, degree of the numerator is 2, degree of the denominator is 2 as well. Then what kind of asymptote, horizontal asymptote, does it have? Okay, this one, the degree of the numerator is smaller. So in this case, x-axis is the horizontal asymptote. Okay, but here degrees are equal. Okay, then what's going to happen if the degrees are equal? It says if the degrees are equal, then the ratio of the leading coefficient of p and q is the horizontal asymptote. Because p and q are polynomials. This p has a leading coefficient. This one he has also a leading coefficient. You see, like this example here, the leading coefficient is 5, leading coefficient is 2. Leading coefficient is 3, leading coefficient is 4. See, leading coefficient is 3, leading coefficient is 5. So leading coefficient is the coefficient of the term with highest degree or highest power. If the degrees are equal, if p and q have the same degree, let's say p is degree 5, so is q. P has degree, let's say 2, so is q. So if the degrees are equal, then you say y equal to the ratio of the leading constant coefficients. Leading coefficient of p and q is a horizontal asymptote. Okay, we're gonna do that in just a second. Let me just do this last case. If the degree of p is bigger than the degree of q, then the rational function does not have a horizontal asymptote. It has maybe a slant or parabolic or more complicated asymptotes. We will not study this case in this course. So you learn how to find the horizontal and vertical asymptotes only. Okay. And understand the meaning of vertical asymptote for other animals. Okay. let's see. We're going to go to examples and see what happens. If the degree of P is bigger than degree of Q, then you don't have horizontal asymptote. You have so-called slant asymptotes, and we are not going to do that. Okay, so we are not going to consider this situation. If the degree of P is bigger than that, we simply say no horizontal asymptote. Okay, let's look at some examples. Okay, so let's look at some examples here. Here we go. It says find and draw the horizontal asymptote of the given functions. Okay. You see, degree of the numerator. So this degree equal to 2. You see, degree equal to 2 as well. You see, let me just circle them with red. This is degree 2 and this is degree 2. So both have the same degrees. Degree of P equal to degree of Q. So that means what? Y equal to, the leading coefficient is 3 in the numerator, the leading coefficient is 4 in the denominator. So I say 3 divided by 4. 3 divided by 4 is the horizontal asymptote, which is 0.75. Okay, so if this is let's say 1, 2, 3, let's say this is 1. If this is 1, okay, then 3/4 is 0.75 is right there. Y equal to 3/4. That's your horizontal asymptote. Now if you want to find the vertical asymptote, you have to put the denominator equal to 0. Okay? So if you put the denominator equal to 0, I think just maybe for the sake of it, let me just go like this. Put 4x squared minus 16 equal to 0. Then if you divide by 4, you get x squared minus 4 equal to 0. You get x equal to plus or minus 2. These are the vertical asymptote. So here we go. 1, 2. This is one vertical asymptote. Minus 2. And this is, I count 4 of them as 1. 1, 2, 3. And 3 of them as 1. 1, 2, 3. 1, 2, 3. So this is 2. Negative. Then 1, 2, 3 is 1. 1, 2, 3 is 2. So my 1 are not the same on x-axis and y-axis. So here we go. For this function, you see, you have x equal to 2. We have one horizontal asymptote of y equal to 3/4. And you have two vertical asymptote at x equal to minus 2 and x equal to 2. Okay. This next example, this is degree of the numerator of P is equal to 1. See, the degree is 1. The degree here is 2. Degree of Q is 2. So 1 is less than 2. The degree of P is less than the degree of Q. Remember what it said? If the degree is less than, see, if the degree of P is less than degree of Q, then x-axis is the horizontal asymptote. So here we go. In this case, y equal to 0, which is x-axis, is the horizontal asymptote. So it's like right here, you see. I'm not gonna do a vertical asymptote for this one because I don't have enough room to do it. it has two vertical asymptotes. I don't know where they are. Maybe somewhere one there. See, actually, let me see if I can factor it. Can I factor that denominator? Let's see. I have to put the denominator. Let me just maybe do it right here. Here we go. Put the denominator equal to 0. 2x squared minus 7x minus 3 equal to 0. Let me see if I can do it on a scratch paper because I don't want to mess up my space here. So if I have 2x and x, then I have to have 3 minus 3, so I minus 3 plus 1. Well, plus 3, 6, no, minus 1, plus 1. I don't think I can factor this. So let me see. Let me just do something quickly in my mind to see if it's worth of going through 49 plus 24. No, it's not factorable, so I'm not going to do it. Okay, so I don't want to do it because the answer is not nice looking. Okay, so let's not do it. Let's not do the vertical asymptote. If I give you something for vertical asymptote, I would give you something that is nice. You can actually either factor it, or when you use quadratic formula, you get nice answer. Here you won't get nice answer, so I'm not going to even try it. Okay? I don't even have room to do it. So finally, this last one. You have a degree of P is 3, degree of Q is 1. You see, this is 3 and this is 1. So 3 bigger than 1. So this is the third case, and the degree is bigger. So no horizontal asymptote. You may have, in this case, you have a slant asymptote, so no horizontal asymptote, and that's it. That's all, as far as I would go. All right. So we have done a lot with rational functions. So the last topic is this: how do I use all these informations that I have accumulated about rational functions to sketch the graph of the rational function without a graphing calculator? Because we can always graph it with a graphing calculator, but even with graphing calculator, we should understand what's going on as well. So to graph rational functions, we do it in about 6 steps. You know, step 1, you find the domain. When you find the domain, you find the vertical asymptote at the same time. Okay. The second thing you do, you find the y-intercept, just like you always do for any function. Step 3, you find x-intercepts. You always do that as well. Then, if necessary, you construct a table of values, a few extra points on the graph. Like you put x equals to so much to see what the y value is. What x value depends, you know, what x value helps you to get the graph. So you get it. So you prepare a table of values, not really big, like maybe 2 or 3 points at most. And then you put all this information to above right here, step 1 through 4. You put them on XY plane and draw the picture. And then after that, you do it with your graphing calculator to see if you did it right. Okay. So let me perform these steps for 2 examples here, so you get some idea, and then you can do it with the graphing calculator at the same time in the future. Okay, so this is your function. Okay, so what is it? Domain and y-intercept. So here I would say 1. Set the denominator equal to 0. So is it x equal to 2 is right here. But let me see what I want to find. 3, so let's say 1 and 2. This is 2. So the domain is everything to the left side and everything to the right side. So domain, set of all x's that x is not equal to 2. So it's minus infinity to 2 union 2 to infinity. That's the domain. Now what is it? Vertical asymptote. So vertical asymptote is x equal to 2. So where is the point missing here? The dry vertical line right here. X equal to 2. See? So I found the domain and I found the vertical asymptote. Where's the next one? Find y-intercept. How do you find y-intercept? 2. Y-intercept is always f of 0. So if I replace a by 0, you get 3 times 0 minus 3 over 0 minus 2, you get 3 half. So y-intercept is 3 half. So if this is 1 half, this is 1. So this is 1 half, 2 half, 3 halves here. So this is the y-intercept. So this is 1 actually. See? This is 3 half, 1 and 3 half is 1. This is half. This is 1 and half. So this is 3 half. 3 half is 1.5. So this is 1 and then 1.5. Each unit is half. So half and half is 1 and half. Okay. X-intercept. As we said before, you put the numerator equal to 0. Solve this one for x, you get x equal to 1. X-intercept x is equal to 1, so it's right here. See? Right here, 1. Okay. Then what is the horizontal asymptote, by the way? Horizontal asymptote. I should do it on step 1, so let me do it here. Horizontal asymptote. The degree of the numerator is 1, you see? Degree of the numerator is 1, degree of the denominator is 1. The degrees are equal. So, degrees equal. When I say degrees equal, I mean degree of the numerator and denominator. So, y equal to the ratio of the leading coefficient, 3 in the numerator and 1 right here in the denominator, so I get 3. So horizontal asymptote is 3. I guess my unit is way too big because I'm running out of let me change my units here a little bit so I can actually, so let me change this point here for a second. I have 1, 2, 3, 1 and half is right here. This is 1 and half. This is 1.5. This is 3/4. I mean 3 half. But this is the y-intercept. I changed it. I'm using each unit as 1. 1, 2, 3 right here. This is 3. Horizontal asymptote is at 3. So y equal to 3. And this point is the y-intercept. Okay. So I have y-intercept, x-intercept, is 1, y-intercept is 1.5, x equal to 2 is the vertical asymptote, y equal to 3 is the horizontal asymptote. Okay, so I did all I could. Let's see. Actually, I can draw one page, one piece. You see, your graph goes through this point and this point. As you go to the negative infinity, the definition of asymptote, the graph of the function should become horizontal. Okay, so let me make my asymptote green so I can draw my graph in red. If I can find my, here you go. So the graph of the function goes through this point and this point, and as you go through this point, you go to the left, it's going to slide against this line, like this. Okay, and then as you go to the right, approaching this vertical asymptote, going to slide against it like this. You see, so you get one piece of graph like that. And then this another one, because this is a vertical asymptote. As I said, there is one piece of graph to the left. There must be one to the right. How do I get the one to the right? I have to do a table of values. So I say table of values. Let's put right here x and y. Because it's on the right side, I have to use numbers bigger than 2. So I'm going to try 3. To put x equal to 3 right here. If I put x equal to 3, maybe I can do it right in the margin. You see, if I put x equal to 3, what do I get? 3 times 3 minus 3 over 3 minus 2. So what would I get? 3 times 3 is 9. 9 minus 3 is 6. Over 3 minus 2 is 1 is 6. So I get 6. So at 3 you have 6. So here we go. Where is it? 3. 1, 2, 3, 4, 5. Maybe we erase this, put it there. Move it to a different location. God, this thing doesn't work. There we go. This is a line x equal to 2. So at 3 I have 6. 1, 2, 3, 4, 5, and 6 is right there. Of course, my asymptote is going like that. So passes through this point. You see. So this is 3 and 6. So the graph of the function, you see, goes through this point. See, I'll put it here. At x equal to 3, you have y equal to 6. 3 here, 6 right there. So 3 and 6 gives you this point. So the graph goes through this point. So what's going to happen? The graph goes through this point. As you go to the right, you become horizontal. So it's going to go like this. As you go to the left, it becomes vertical. Like that. You see? So you have two pieces, one here and one there. And they are symmetric with respect to this point right there. The point of the intersection of asymptotes. So now if I put this in my graphing calculator to see if I can get it, let me make it bigger a little bit. Y equal to, so put parentheses, so I say y equal to parentheses 3x minus 3, divide that by parentheses x minus 2, like that. And then I'll use window, let's see, I use window minus 4 to let's say 8. And y I use from let's say minus 3 to let's say 8 again. Let's say graph. See, here's one, here's another one. Just like that. Looks exactly like what I have here. See. Let me make this smaller a little bit so you can see them simultaneously. but you don't see the asymptotes. You can manually put the asymptotes in there because I know what they are. X equal to 2 is the vertical, y equal to this. So how do I do that? So let me show you. If you want to put horizontal asymptote, that's a vertical asymptote x equal to 2. Go to program, second program, which says draw. You see, second program gives you draw. So I say second program, it gives you this menu, and this menu, I want vertical, so go to vertical, number 4. So if I choose number 4, vertical, you see, then I can move to the left and right. As I move it to the left and right, and look at the x value, you see, look at the x value on the left, just move it to the left, because x equal to 2 is your vertical asymptote, just move it to the left until you see 2, like that, you see, x equal to 2. Sometimes you cannot get it exactly at the number you want, so you just by a little bit going to the left and right, you get it as close to actual value as possible. So after you put it here, say enter to solidify it. Then you want to do the horizontal, go to second program again. Now use number 3 horizontal, you see, with this arrow up or down, now you can move it, you get the horizontal line, you can go up or down. You see, as you do that, look at your y value and make sure it shows 3. You see, if I go down, it's 2.85. If I go up, it's 3.03. Seems like I cannot get it on exactly at 3. But which one is closer to 3? 3.03 or 2.85? To me, 3.03 is better. So I just leave it there. So I send it. So I enter. You see? So that's it. That's a graph of this function, which is exactly like what I have here. You see? So pretty cool. One last example. 2 more. This is one more and then another one. You want to do this one? So let's see. Make this smaller. I'll make it bigger. This one. Okay. Let's do this example. First, I put the denominator equal to 0. 1, x squared minus 3x minus 4 equal to 0. I can factor this actually. X minus 4, x plus 1 equal to 0. So I get 2 values, x equal to 4 and x equal to minus 1. So these are the asymptotes. Horizontal asymptote. -1 and negative 1 and 4. So -1, and this is -1 right here. Let me see how many units I'm gonna get. It's 4. Yeah. Let me use you see 1, 2. I'm gonna use 2 of these divisions at 1 on horizontal axis. Okay. So let's see, 1, 2. No, it's too big. Just use each one. So I need -1 is right here. So this is, so you have 1 vertical asymptote at this point, -1. This is x equal to -1. This is 1 vertical asymptote, and then the other one is 4. So I say 1, 2, 3, 4. So you expect 3 pieces of graph, 1 on the left, 1 in between, 1 to the right. So, and domain, what is a domain? Domain is everything except those two numbers. So domain is everything to the left, everything in between, and everything to the right. Not those 2 numbers. Okay. So I say domain is minus infinity to -1, union minus 1 to 4, union 4 to infinity. This is minus 1 and 4, right? Horizontal asymptote, you see, the degree of the numerator is 1, so 2, well, still in 1. Degree of P is equal to 1 less than 2 equal to degree of Q. So degree of the numerator is smaller, that means X axis is the horizontal asymptote. Okay, so right here, x-axis, or y equal to 0. Then y-intercept. What is the y-intercept? So let me use this one here. Y-intercept is g of 0. G of 0, if I put 0 everywhere, I get, see, you get 0 here, 0, 0, you get negative 8 over 4. Negative 8 over 4 is just 2. So 2, where is 2? 1, 2 is right here. That's your y-intercept. X-intercept. X-intercept, put the numerator. This is y-intercept, by the way. X-intercept equal to what? Put the numerator equal to 0. Okay. You can put this numerator equal to 0. 4x minus 8 equal to 0, x is equal to 2 as well. Here we go. This is 1, this is 2, it's right there. So x-intercept is 2, y-intercept is 2. Okay? And that's all I have so far. I can graph one piece, I can graph the piece in between. Why? Because see, the graph goes through this point and this point, and I'm gonna slide against these two lines. So the only opportunity, the only possibility is something like this. See? As you go to the right, slide against this. As you go to the left, slide against that. So that's the piece in between. Now how about the piece on the right side? I need some table of values. To get the one on the right side of 4, I'm going to use value x equal to 5. X, y. Put x equal to 5. What do I get? Put x equal to 5 here. Let me just do it right here. X equal to 5. G of 5. What is G of 5? G of 5 is 4 times 5 minus 8. 5 squared minus 3 times 5 minus 4, what would I get? That 4 times 5 is 20, 20 minus 8, 12. 5 squared is 25. 3 times 5 is minus 15. Minus 4. You see, 15 minus 4 is minus 19, you get 6. So you get 12 over 6, which is 2. Okay, so at 5, y is 2. So at 5, here we go, 5, 1, and this 2 is right there. This is 2. So the graph goes through this point, you see. If you go to the left, slide against this vertical line, and if you go to the right, because horizontal axis is x-axis, slide against this line. So it's going to look like this. See? Now if you want to get the one on the left side, I have to use the point, this point is negative 1, so I'm going to try negative 2 right here. This is negative 2. This is x equal to negative 1. So what do I get if I put x equal to negative 2? What would I get? If I put x equal to negative 2, here we go, let me just do it right here. X equal to negative 2, g of negative 2 means what? Put all of these x's by negative 2. So I have 4 times negative 2 minus 8 divided by negative 2 squared minus 3 times negative 2 minus 4. So if I simplify this, what would I get? Negative 4 times 2 of negative 4 is negative 8, negative 8 is negative 16. 2 squared is 4, 4 cancels 4, and 2 times 3 is 6. So it's 16 over, negative 16 over 6, which is about negative 8 over 3. Okay, and if I use my graphing calculator, let me see, approximate 8 over 3, let's see. 8 divided by 3, I get about 2.7. So negative 2.7. Let me see if I did it right. Negative 2, I'm replacing x by negative 2 here. So I get 4 times negative 2, negative 8, negative 2 squared, 3 times negative 2 minus 4. So I get negative 2 is 8, it's negative 16, 4 and 4 cancel out, I get 6. So yeah, that's right. So negative 2.7, where is negative 2.7? This is 2.5, 2.7 is here, so right here, this point. Okay. So this point, so the graph goes through this point. This is point negative 2, negative 8/3, right here. So as you go to the left, you slide against this line. As you go to the right, you slide against the vertical line. So the graph looks like this. So I have 3 pieces, you see. Now let me do it with the graphing calculator to see if I get the same thing. So I have parentheses 4x minus 8, divide this by parentheses x to power 2 minus 3 times x minus 4. Okay, so I want to use the window minus 8 to 8. That's good enough. And then y I'm going to use from minus 8 to 8 as well. Big enough to show everything. So say graph. And it's similar to this. You see, it's similar to what I have on my paper. Okay, but you don't see the asymptotes. You see the horizontal asymptote because it's x-axis. How about the vertical asymptote? You have 1 at negative 1, 1 at 4. You can stick him in there. So I go to second program, which is draw. I go to number 3, horizontal. Then well, I don't need horizontal because horizontal is the x-axis. So second program, I go to vertical, which is number 4. Then you see, I can go back and forth. I put 1 at negative 2. Look at the x value. Negative 1, I'm sorry, negative 1. You see negative 1, negative 1.02, 0.85. I think negative 1.02 is good. Closer to 1. So say enter. Then go to the right, and then the next one is x equal to 4. Look at your x value and stop at 4 or close to it. You see 3.7, 3.9, 408. is better than 3.91. Yeah, I don't know which one is better. It doesn't matter really. One of them. That's it. Say enter. Then you have the graph of this function, which is exactly like the one I got on my paper. You see, this is what I have on paper, and this is what I have my graphing calculator. Okay. So let's do one more example, and then we are done with this section. Okay, let's do one last example. There are two application one, but I'm not gonna do it. So here we go. Let's do this one. We can do this next one. It's not very difficult. The next one. What is the next one? I'll let you work on the next one. Okay, let's see. Put the denominator equal to 0, x squared minus 2x minus 3 equal to 0. You can factor this. X minus 3, x plus 1 equal to 0. You get x equal to 3 and x equal to minus 1. These are your asymptotes. Here we go. X equal to minus 1. These are the vertical asymptotes. So you have three regions, so you expect three pieces of graph. And horizontal asymptote. What is the horizontal asymptote? See, degree. Okay. Degree of the numerator equal to degree of the denominator. So that means y equal to the leading coefficient. 3 divided by 1, which is 3, is a horizontal asymptote. So let's see. I'm going to use these at 1. 1, 2, 3. 1, 2, 3. This is the horizontal asymptote. Okay? Then domain, of course. Domain is this piece together with this piece together with that one. So domain is, let me write it down, minus infinity to minus 1 union minus 1 to 3 union 3 to infinity. Okay. And y-intercept, I guess y-intercept is number 2. I lost the numbering, which doesn't matter, 2. Y-intercept is equal to h of 0. And h of 0 is 6 over negative 3, which is negative 2. So here we go. This is negative 1, negative 2. This is y-intercept. Okay. 3 x-intercept numerator equal to 0, so you get 3x squared plus 6 equal to 0, but it's impossible. Because 6 is positive, whatever you choose for x, x squared is positive, so the left side is positive, so it's never 0. This one is never 0, so I shouldn't say impossible. But I said, let me rephrase it. Put the numerator equal to 0, but numerator is never 0. So that means no x-intercept. So how does this look like, really? See, the graph goes through this point, and it slide against this line, and it slide against that line. It cannot go up. If it goes up, it would cross x-axis, but we don't have x-intercept. So it has to go through this point and then turns down to miss x-axis. You see, you cannot go this way. You see, you cannot go like that. If you go like that, then you get x-intercept. If you go this way, you get x-intercept. If you go this way, you get x-intercept. So it cannot be any of these. The only possibility is this one right here. You see, slide against this, comes down and slide against that, and then misses x-axis. Okay. Now, how about the pieces on the right side? This is 3, so I'm going to try 4. Put x equal to 4. Put x equal to 4, and for the left side, put x equal to -2. So if I put x equal to 4, what would I get? If I put x equal to 4, I get 3 times 4 squared plus 6 over 4 squared minus 2 times 4 minus 3. So what would I get? 4 squared is 36. 3 times 6 is 48. 48. 54 over 4 squared is 16. 8, 11, 16, you get 5. So 54 divided by 5, what is that? 54 divided by 5 is about 10 point something, okay? So let me see if I did it right. Put 4, right, 4. If I put 4, I get 3 times 4 squared plus 6. 4 squared minus 2 times 4 minus 3. 4 squared is 16 times 3 is 48. 48 and 6, you get 54. Then 4 squared is 16. 2 times 4 is 8. 8 and minus 3 is 11. 16 minus 11, you get 5. Then 54, let me see again my graphic. Let me use my calculator. 54 divided by 5, you get about 10.8 or 11. So about 10.8 at 4. So what is that? At the 4 is 10.8 is somewhere right here. You see, somewhere here. You get the point, 10. Because you see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I don't have room. So the graph of the function goes through this point and slide against these two lines, so it goes up like that and comes back down. Just draw it like this here. You see, like that. Goes up this way and then slide against this line. Like that. And then another one on this side. If I put -2, what would I get? If I put -2, let me put it right here. 3 times -2 squared plus 6 divided by -2 to the 4th minus 2 times -2 minus 3. So what would I get? -2 squared, 4 times 3 is 12. 12 plus 6 is 18. Then 2 times 4 is 16. 16 minus 14 is 2. 2 minus 3 is minus 1 is minus 18. So minus 18, something like that. Then at -2 is minus 18 is somewhere here. You see, down there, right down here. So the graph of the function looks like this. See? So really, I should have put it bigger XY plane. So let's look at them on the graphing calculator. So let me type it in first. Let's see. Kind of rush through it. It's not a big deal. I just want you to get some idea and being able to actually graph it on your graphing calculator. So I have parentheses 3x squared plus 6, 3x squared plus 6 divided by parentheses x squared minus 2x minus 3, then oh, I didn't move it, sorry. X squared minus 2x minus 3, like that. And then my window, I'm gonna go from minus 8 to 8, which is good. And then y value, see, I need a big y value, so I go from minus 20 to, let's say, 50. I guess I didn't quite. Minus 20. Get positive 18. I guess this one becomes positive 18. This one is positive 18. See, that was my error. Let's see, because you get yeah, you get positive 18. This is positive 18. So instead of this gonna be up here, it's gonna be there. When I put negative 2 here, I should get positive 18. I put negative 18 here. So I put this graph in the wrong place. It should be up there. So that's what I have on my paper, and this is what you get on your graphic calculator. I'm going to stop here on this section. I'm not going to do those two. Maybe just do one and that's it. Let me see what this one is. Let's see. Okay, let's see what this one says. You have this function here. It says for a person with sensitive skin, the amount of time in hours the person can be exposed to the sun without minimal damage can be given by this formula when S is the sun scale, the sensor scale reading. Okay, sensor scale reading is based on the level of intensity of ultraviolet ray. Okay, so this is it. Yes, and this is the amount of time you can be tolerated. You can tolerate sun without getting serious damage to your skin. Okay, it says find the amount of time a person with sensitive skin can be exposed to the sun with minimal when S is equal to 10. What is S? S is sensor scale reading, okay, that may be different from person to person. So for the person with S equal to 10, how long that person can tolerate the sun. With the person with S equal to 100, then what? Okay, the sensor reading is, you know, how intensive the sun is that day. Sometimes sun is more intense than the other days. So sometimes S is 10, sometimes S is 100. Okay, and the person has different sensitivity to the intensity of the sun. Okay, so you just put T of 10. T of 10 is equal to 0.37 times 10 plus 23.8 divided by 10. So what do I get? So I have a point 0.37 times 10 plus 23.8, and then divide that by 10. I get 2.75. So that means if S is 10, if this sun sensor scale reading of the sun is 10 at that day, then you can tolerate the sun for 2 hours and 2.75 hours. Now if S is 10, then 100 value you get, T equal to 100. T equal to 100 is 0.37 times 100 divided plus 23.8 divided by 100. So how much is that? So let's see. 0.37 times 100 plus 23.8, and divide that by 100. You get about 0.608 hours. As you can see, when sun is more intense, sunny day, and sun is really intense, 100, then that's the amount of time in hours, like a little bit over 30 minutes or a little bit over half an hour you can tolerate the sun before you get serious burn in your skin. But if S is 10, which means maybe the sun is not as intense that day, maybe a little bit cloudy out there or something like that, then you have a little bit more tolerance to the sun's, ultraviolet light. Okay. Now the question is this one: if this model is valid and S is bigger than 0, what is the horizontal asymptote tells you? See, as S goes to infinity, what is the horizontal asymptote? The horizontal asymptote means because see, the power of S is 1, then horizontal asymptote is, see, the power of the power of the variable. Instead of x you have s, instead of y you have t. So power of the denominator, I mean the degree of the numerator and degree of the denominator is 1. So the horizontal asymptote is the ratio of the leading coefficient, which is 0.37 divided by 1 is 0.37. So that means as the sun gets more intense and intense, as the scale goes up, then you leveled off to 0.37 hours, almost. Let me multiply this by 60. Let me see. In terms of minute, 0.37 times 60, which is 22 minutes. You see, this is hours, which is about 22 minutes. Okay, so that means eventually, as the sun gets more and more and more intense, and the scale goes up, goes to infinity, as S goes to infinity. That means as the sun gets really, really intense, you cannot be in it more than 22 minutes. That's all you can tolerate. That's horizontal asymptote. So you level off to 22 minutes or 0.37 hours. Okay, that's one example of such situation. And I'm not gonna, bother with the next example. You go ahead and work it out to see if you have any questions. Let me know. I'll be happy to help you. Good luck. So pretty soon we're going to start chapter 3, which is about the concept of logarithms. Okay. So go to your homework assignments. Do all the homework. Listen to all these videos. Once, twice. I think these videos are really helpful because you have control on it, when to watch them and how many times to repeat them, and you can stop it at any time you want, and then go back to it. And I think it's better than better than regular live face-to-face class. Actually, this is what I teach. I go faster in class. Here I'm spending a lot more time and doing in more detail, really. During the regular semester, I don't have enough time to do things as detailed as I do here. So this is really good benefit for you to watch these videos and benefit from them. Good luck, and let me know if you have any